In the previous part, I talked about the foundations of TRIZ. Here in the second part, I'm going to talk about the problem-solving tools that TRIZ has to offer. These tools may not give us specific answers to all our design problems. Instead, these tools will give us some guidance to get the ideas about how to solve our problems. Of course, to get those ideas, you need to have some expertise in the domain of the problem that you're solving. The first problem is categorized as physical contradiction, and the tools that TRIZ offers are physical contradiction resolution and separation principles. To analyze the contradiction, we need these three steps. First, capture the functions. You can use functional models. Second, identify the physical contradiction. 3, identify the zones of the conflict. Is it spatial or is it temporal? Spatial means it is related to space. Temporal means it is related to time. Let's take a look at an example. In this example, ampoule is something that contains medicine. But then this ampoule needs to be sealed. So on the top of this ampoule, there is a burner. They will burn the top part of the ampoule and make it sealed, such that the medicine inside the ampoule will not spill out from the ampoule. So let's follow the previous 3 steps. First, we are going to analyze the functions. So the flame from the burner will transfer useful action from the heat to the top of the ampoule and will seal the ampoule. However, the heat also have a harmful action on the drug that is contained in the ampoule. The drug should not be exposed to the heat, but because of the heat that is going to seal the ampoule, somehow it also heats the drug. So the flame will melt the glass and seal the ampoule. This is useful function, but it also overheats the drug, which is a harmful function. So the contradiction here is that heat is useful to seal the ampoule. Ampoule needs to be hot, but the heat is also harmful because it decomposes the drug, which means that the ampoule cannot be hot. Because if the ampoule is hot, then the drug is decomposed. So there's a contradiction here that the ampoule must be hot, but it also cannot be hot. It must be hot such that it can be sealed, but it cannot be hot such that the drug will not decompose. So number 3, we identify the zone. From the spatial aspect, the heat should be applied to the tip, to the upper part of the ampoule, so to this part, but not to the lower part. So from the spatial aspect, we see that we can separate it in terms of space, that the upper part should be hot, but the lower part shouldn't be hot. From the temporal aspect, however, we cannot make an separation because both useful and harmful functions, they happen at the same time. So now we have identified that the contradiction may be separated in terms of space, in the spatial aspect, because the top part must be hot, but the bottom part must not be hot. Based on the zones of the conflict, TRIZ offer several types of separation. Separation in space, time, between the components, and between components and the set of the components. Now let's see an example. Suppose we are going to coat a piece of metal, with a metal salt solution. So we put the metal into the solution and then we heat everything. the heat will help the process to become faster. However, the end result is that, okay, the metal is coated successfully, but then the metal salt solution is decomposed. It means that the solution may not be good for the next process. What can we improve from this example? Well, if you think about the conflict, the process needs to be hot, but then it is useful to coat the metal, but it is harmful to the solution. So to separate the space, the zone of the conflict in terms of space, now we heat the metal first. So before you put the metal into the solution, you heat the metal. So now only the metal is hot, the solution is cold. And then you put the hot metal into the cold solution such that only the solution that is on the surface of the metal becomes hot. So now the process of coating is successful, but then the solution is also not decomposed as much as before because only the metal is heated, not the entire system. This is an example for separation in time. If you remember this example from the first part in TRIZ foundations, it's about coating a wire through an enamel. So the wire is pulled through an enamel and goes through a die to remove the excess of the enamel and then also to size the wire. So during the process, when we pull the wire, the die must be hot such that it can remove the excess of the enamel and then produce accurate size of the wire. However, if this process stops for something, the hot die will bake the enamel and it will destroy the wire. So there's a conflict here. The die must be hot such that it can remove the excess of enamel and it can size the wire precisely, but then it must be cold as well. When the process stops, when the wire, when something stops the wire feed, it must be cold to prevent the hot die from destroying the wire. So you see there's a conflict here that we can separate by time. It must be hot when the wire is feeding into the die, when it is pulled, but when that feed stops, the die must be cold. So one of the solutions is that, okay, let's put a spring in front of the die. So here in the bottom part, if the wire feed is going on, meaning the wire is pulled, and then the string will be compressed, now the die is in the hot area. See, the die is in hot area. However, if the process stops here, there's no wire feed going on, then the spring is relaxed and you see the die is in the cold area. So the heat from the die will not destroy the wire because now the die is in a cold area. Okay, so by putting a spring here, it may separate the time when the feed is happening, means the wire is moving, and when the wire feed stops. In the next example of separation, we're looking at the bench vise. So these type of vise usually are designed to hold objects with regular shape. When the object shape is irregular, usually you need to make a special jaw such that it can hold the object tightly. So the contradiction is that the jaw must be rigid so that it can clamp the object, but they also must be flexible to accommodate different types of part shapes. So the solution here is that we are using what they call as loose body here. So you put it in the upper jaw and lower jaw, and then these loose body are filled with loose materials. Then you put the workpiece in between the loose bodies. And then once you already put the workpiece, use the vacuum pump to set this loose body exactly following the shape of your workpiece. So now you do not need to design a special jaw, but now you can hold the irregular shape tightly. In the next example of separation, we're talking about a remote control. So in the remote control, you have a capacitor and you have also a battery as the power source. So we would like to have a high power remote control, means that you can use it from a distance far enough from your TV, let's say. To have such remote control with good power, we need a high value capacitor. However, a high value capacitor usually drains the battery a lot. So the contradiction here is that we want to reduce the leakage of the current, means that we want to conserve the battery, but we also want the power of the remote, means that we want to have high capacitor value. Because if we use low value capacitor, we conserve the battery, but the power is not good. So there's a technical contradiction here. We want to reduce the leakage current, but then if we do that, the power will become worse as well. So we want to improve the conservation of battery, but then the power becomes worse. If we look at the physical contradiction, actually we can say that we can just look at the capacitor itself. The capacitor should be in low value when it is charged. Means that when you are not using the remote, it should be in low value so that it will not consume the battery power. But then it should be in high value when it discharges. So when you are using the remote, the value of the capacitor should be high. But when you're not using the remote control, then the value of the capacitor should be low. So that's the physical contradiction. So now the solution is, instead of using one capacitor, you are using a set of low value capacitors, such that when you are not using the remote control, they will not really drain the battery. However, when you are using the remote control, the value of these small value capacitors will be combined to generate enough power. So in the previous part, we are looking at problems that can be categorized as physical contradictions and the tools that can be used to solve them. Now let's see if the contradiction is technical contradiction. The tools that TRIZ offers is called Inventive Principles. So when Altshuler did his research, he identified 1,250 typical technical contradictions. And using 39 design parameters, he can express those contradictions into a 39 by 39 matrix. We'll see this in the next slide. And then, interestingly, to solve all those contradictions, TRIZ offers 40 inventive principles. So to solve this more than 1,000 typical contradictions, TRIZ can offer that you can get the idea to solve those contradictions with using these 40 inventive principles. Remember that they do not offer a direct solution, they only suggest the most promising directions. And as I said in the beginning, if you want to solve the problems by TRIZ, of course you need to have some expertise in the domain. So this is how the matrix looks like. So all the rows here, there should be 39 rows with respect to 39 design parameters. And there are also 39 columns here with respect to 39 design parameters. So to use this table is first we are looking at the rows, what should be improved. So we are looking at which parameter that should be improved. And then in the column, we are looking at which parameter will deteriorate, means that which parameter will become worse in our problem, in the contradiction. Remember, because in the technical contradiction, we want to improve something, but then the other parameter becomes worse. So to read this matrix is we see what we want to improve in the row and what will become worse in the column. And then let's say we're saying we want to improve parameter 5, but then want to improve parameter 5, but then parameter 9 will become worse. And then TRIZ suggests these 4 principles to solve your problem. Okay, so you're saying you want to improve area of movable object, but the speed becomes worse. TRIZ says try these principles, 29, 30, 4, and 34. Let's see a concrete example. Suppose you are going to take off a nut using a wrench. The problem here is that this area of the nuts, they get concentrated load such that the nut will wear out quickly. Is there anything we can do to solve this problem? We look at the inventive principle table and we say that we want to improve the reliability of the process. However, if we improve the reliability, the ease of the operation will become worse. So TRIZ says that try these 3 principles. Let's see what those principles are. Principle 17, another dimension. Principle 27, cheap short living. And principle 40, composite materials. In this case, what we can do is we are using a soft metal or plastic pad to put in between the wrench and the nut. Because this pad is soft, so it will not really wear out the edges of a nut. So again, how do you know that these principles correspond to that solution? I think you really need to have some expertise in this area, and then you also understand all the design parameters in the inventive principles table, and then you may try to get some ideas and then implement it in the design. I know it's not easy. Now remember that sometimes we do have the functions, but they are imperfect. Either the useful functions is inadequate, or we have excessive harmful functions. For these types of problems, TRIZ suggests us to use functional improvement methods and TRIZ standard solutions. First, if we have inadequate useful functions, we would like to improve that useful function. The first method is filling the missing element. Suppose at the beginning you only have the object. According to TRIZ, what you need to do is you are adding a subject and the action. So for example, you have vapor bubble on the liquid that you want to separate. So TRIZ suggests you to add a rotation device that gives mechanical force such that it can separate the bubbles from the liquid. Now sometimes you already have the subject, but the useful function from subject to object is not enough. So what TRIZ suggests is that we are adding another subject that giving another function. Let's see an example. Suppose we are using a hand tool to remove wallpaper from the walls. However, sometimes it is still difficult to remove the wallpaper. So it is suggested here we are using an additional steam sprayer to steam the vapor so that you can remove the wallpaper more easily. When the useful function from the subject to the object is not enough or inadequate, sometimes we can alter or change the object, such that now the same function is enough. How can we change this? How can we change the object? We can replace the original object by a new substance. We can modify the substance of an object, apply additive to either outside or inside the object, or change the material or properties of the object. Let's see how this works. Suppose you are going to detect the leakage in a refrigerating unit. It is hard to detect where the position of the leakage using an eye. So it is hard to see with your eye which part of this unit is leaking. So then what we can do is we paint this refrigerating unit using a paint that will react with the liquid from the leakage. So now whenever there is a leakage, you can see it from the color because the paint will react with the liquid. So now you can see by the change of the color, you can detect, okay, so that's where the leakage happens. So this is how we're altering an object. When the useful function is inadequate, sometimes what we can do is we can also alter the function or the field. Let's see how this works. In the production of semiconductor wafer, we use infrared lamp. If the beams from the lamp is uniform, like the first picture here, then the edges of the wafer, it cools down quicker, such that the quality is not very good. So now we alter the field, we alter how this infrared lamp produce the beams, such that now we have more beams that goes through the edges of this wafer, such that now it cools down faster, but it's compensated by more beams that are going to that part. So now the quality of the wafer becomes more uniform. Now let's see what happens if we have harmful functions. The first method is we're trying to block or disable the harmful function. So you can see here we have a harmful function, but then we try to block it. So one of the example is the ampoule example, where we want to seal the ampoule using the heat from the burner, but then the heat will decompose the drug. So to block the harmful function from the heat from the burner, we put the ampoule in the water. So the water will absorb the excess of the heat from the burner, such that the heat will only seal the tip of the ampoule, but it will not travel far enough to decompose the drug inside the ampoule. So using this way, we're blocking the harmful effect of the heat from the burner. We can also eliminate or contain harmful functions by adding another field to counteract with the first harmful function. So the example here is that suppose we are trying to pollinate flowers. We blow the air with pollen to the flower. However, the problem is sometimes the petal of the flowers, they will not open. So the pollen will not reach the inside of the flowers. What we can do is that it is suggested here, we first pre-charge the flower with an electrode. And then when we are going to blow the pollen into the flower, we are using another electrode with the opposite charge. So let's say the first is positive charge. Here we're using another electrode with negative charge. So then now the petals of the flowers are open, and then we blow the air with the pollen to the inside of the flower. The next method is we can try to divert or draw the harmful action or field to the other object. Here, if we have a lightning rod on the top of a building, the lightning will strike the rod, and then this rod will divert the harmful action from the lightning to the ground instead of to the building. The next method is we're trying to trim or replace the subject of a harmful action. So as an example here is that you want to grind the internal part of this part. So you want to grind the inside. So we put some abrasive particles inside this part, and then outside you're using the rotating magnetic field to move around the particle inside this part. So the particles will grind the insides of this part. However, the thickness of this part weakens the magnetic field that reach inside the part. What we can do is that we want to reduce the effect of the thickness of the walls of the part. So we preheat the part such that the magnetic characteristic of this part is weakened, such that now the magnetic field can reach stronger into the insides of the part, where you have the abrasives that is working here, grinding the part more effectively. In the previous method, we trim or replace the subject of a harmful function. We can also trim or replace the object of a harmful function. In this example, we're trying to remove allergens from milk. We heat the milk and let it cool down such that the allergens are settled down. And then we collected these allergens. But apparently there are some allergens that are not settled out using this method only. So what we can do is we're adding calcium chloride into the milk such that now there are more allergens that can be captured after the milk is cooled down. Sometimes the problem lies in the fact that our systems is too complex. So TRIZ suggests us to do trimming and pruning. Trimming can be used to eliminate redundant functions. To identify redundant function, we can draw a functional analysis diagram, and for each function we ask, is this function really needed? What kind of parts should be trimmed? The parts that deliver no useful function, many harmful functions, and only few useful functions? The function that offer low value to customers, the function or the parts that have low utilization ratio. So these are the parts that you might think of trimming. For example, in the 70s, when the Soviet Union wanted to launch a lunar probe to the moon surface, they have a problem with the light bulb. They need the light bulb, well, actually they need the light to illuminate the lunar surface ahead of the vehicle. However, the bulb will not survive the impact of the landing. So they were trying to think how to design the bulb such that it can go to the moon and illuminate the surface. So somebody called Dr. Babakin asked, what is the purpose of the bulb? The answer is to vacuum seal around the filament. However, when you're going to the moon's atmosphere is already vacuum. So therefore, he suggested that we can use the lamps without the bulbs. This is called identifying a redundant function. And now we can trim the bulb and have a bulbless lamp. The last type of problem is when we have our system is doing its job, but we need enhancement. So TRIZ suggests us to look at the evolution of technological systems. The first pattern in the evolution of technological system is we're trying to increase the ideality. Remember, ideality is the division of benefit by the sum of cost and harm. So what we can do to increase the benefits? First, you may increase the number of functions. It is called mono, bi, and poly evolution. If you think about cell phones, at first it can only serve the function to call the other phone number. And then it has more function. You can put some text. And then now it has poly function. It has a lot of function in a smartphone. So it follows the mono, bi, and poly evolution. If you don't increase the number, you can also increase the magnitude and quality of a function. For example, you increase the resolution of your camera, you increase the capability of the camera to take picture in the low light environment, and so on. So you keep increasing the quality of the same function. We can also increase the ideality by reducing the cost. So the example here is that when we have let's say a greenhouse, when the house gets too hot, we should pump some water to cool this greenhouse a little bit. However, to reduce the cost, what is suggested here is that we are using an expandable liquid on the roof of this greenhouse. So when the temperature is hot, when the weather is hot, the liquid will expand and then it will automatically trickle down into the greenhouse. It eliminates the cost from using the pump. The evolution of technology also follows several other patterns. For example, keep increasing the complexity, and then it will follow by simplification. And then there's also a pattern that among all elements in your system, they will have non-uniform development. Means that some parts may be already on their mature stage, the other parts are still at the very beginning of the technological evolution. And then the last pattern is we are trying to increase the degree of dynamism. For example, at first the camera lens can only take the picture from a certain distance, but then after a while the lens becomes more dynamic. It can be adjusted to take pictures from different range of distances. So that's the end of this presentation about TRIZ problem solving tools. Thank you.